Okay, welcome to today's lecture. And I want to start today by looking a little bit at noise and regularization for computerized tomography. And we started the lecture with several regularization techniques. And you might ask, well, what's the regularization type that we have here? And where's the regularization parameter? And we'll clear this up. I will do that by looking at noise amplification from a statistical viewpoint, which is what usually also happens in practice. Okay, here's our problem. We have G equal to RF. G is the radon transform, so G is the undisturbed radon data. What we measure is some G tilde, which is equal to G plus N, where N of theta and S is a random variable, and that means that G tilde is a random variable as well. We assume that for every fixed theta and S, the expected value of the error is 0. And we also want to measure the error in the measurements by looking at the variance. So the higher the variance is, the higher the error that we have. And we assume that the variance for fixed theta and S is the expected value of n squared of theta and S. So that should be sigma squared of theta and S. And the covariance for theta not equal to theta prime, S equal to S prime should be 0. So we assume that the measurements that we have are uncorrelated, that we have uncorrelated noise. And if you have problems with these continuous statistical random variables, then just think of them as discretized, and then it doesn't make a difference. Okay, so finally we have that the expected value of n of theta and s and n of theta prime and s prime is sigma squared times delta of theta minus theta prime and delta of s minus s prime in our distributional setting. Okay, now since G is unknown, all we can do is plug in G tilde in our reconstruction formula. So we have something like integral over Sn minus 1, integral over R, G tilde of theta and S, V of x times theta minus S, where V is the filter that we have chosen. That includes the cutoff frequency omega, ds, and d theta. Okay, and the result we call f tilde, and of course for every x, since g tilde is a random variable, now f tilde of x is also a random variable. Okay, so it makes sense to look at the expected value at the point x. But since this is linear in G tilde, it's also linear in n. So when we take the expected value over here, that becomes the expected value of G plus the expected value of n. G is fixed, so that's the expected value of G stays G. Expected value of n is 0. So this is just the expected value that we have is just the undistorted reconstruction of G, and this is exact if omega was if f was omega band limited. That's all that we proved. Okay, but we are interested in the impact of the error. So we're interested in the variance of E f tilde of x. So the variance at point x, sigma squared of x, is given by the expected value of f tilde of x minus E f tilde of x squared. And I think I always do that wrong. There should be, of course, another bracket around here. So that's the expected value of f tilde of x minus expected value of f tilde of x squared. And but we have the difference between f tilde and ef tilde is just the reconstruction of the noise function. So plugging this in, this means that this is the integral over Sn minus 1 integral r n of theta and s v of x times theta minus s ds d theta. That's one of these, and that one squared over here. Okay, because n is just g tilde minus g. Okay, squared, that should be squared, so I'm writing it down a second time. And now, since the expected value is linear, we can take all these integrals out. And what's left is a fourfold integral times the expected value of n of theta and s, n of theta prime of s, and then times v of x theta and s, and so on. So all these filters that we have here accumulated. Now, the only thing that's a random variable here is the n. So we can look at this guy over here, and we already noted, we assumed that the measurements are uncorrelated. So these are delta functions in theta minus theta prime and s minus s prime. So this is nothing but sigma squared times delta theta prime delta of s minus s prime. So this vanishes for theta not equal to theta prime and for s not equal to s prime. And when it's the same, it's sigma squared. So all that's left is an integral Sn minus 1 integral over r f squared, v squared of x times theta minus s, because these are now the same, and sigma squared of theta and s ds d theta. And here I permit that sigma depends on theta and s. But now we assume that wherever we measure, the variance is the same. Then sigma squared of theta and s is just sigma squared. And then we can take everything out. This goes over here. And now v squared of x times theta minus s, this is just a shift of the function v. But since we're here integrating over all of r, so we can just write this as an integral over r v squared of s ds. This is constant, and I lost the sigma squared over here, I just noticed. And now the inner part does no longer depend on theta, so this is just the size of Sn minus 1. Okay, now what we can do, and I still lost the sigma squared, and I even, okay, now I see. Sorry, choosing sigma as a integration variable and as the variance was a bad choice. So I just corrected this. And let me restart over here. So we have integral over Sn minus 1, integral over r v squared of s ds times sigma squared. Now the integral over v is the same as the integral over the Fourier transform of v. And plugging this, so the L2 norm of v is the same as the L2 norm of f hat. So I can plug this in over here. And now we have v hat over here, and we can just plug in the definition of v hat, which we already derived in 6.10, and which we used in 6.10. And doing that, we arrive at the final formula that the variance of the reconstruction in a fixed point is given by sigma squared times the integral over Sn minus 1 times a constant, which I didn't write down, integral from minus omega to omega, absolute value of tau to the 2n minus 2, and phi hat of tau over omega squared d tau, where phi hat is the design function that we used to construct our filter. Now, in the simplest case, phi hat is just the cutoff function, so it's the characteristic function of the interval from -1 to 1. So this over here is 1 on the range from minus omega to omega. And that means this is just absolute value of tau squared, and the antiderivative is tau over 3 to tau to the 3 over 3. So that integral is something like omega cube, and we have some prefactors over here times 24 pi square, it turns out. Okay, and that's the amplification factor. So the true error will be bounded, or the variance of the error will be given by omega cube over 24 pi squared times sigma squared. Okay, so we see that the variance of the image, which is finally our error, is given by is an amplification of the original error, of the original variance, and the amplification is bounded by more or less by omega cube. Okay, so we immediately notice what happened. The higher we choose omega, so the higher the bandwidth we would like to reconstruct, the higher the amplification factor for the error is. And now we immediately recognize what kind of regularization we have. First of all, we have a regularization of projection type. We regularize by choosing the bandwidth omega and reconstructing only in the space of band-limited functions. And it's clear the regularization parameter is the bandwidth omega. If omega is large, we have a large projection space, so we get a good reconstruction. We can get good approximations of our function f, but we also get a high noise amplification. It goes with omega 3 over here, omega to the 3 over here. On the other hand, if omega is small, we have a small reconstruction space, and we typically get a worse reconstruction, but we have a much smaller noise amplification. So depending on the quality of the data, we have a trade-off here that the designer of a computer tomography device has to take into account.